Hello, my AP Stats people. Just want to let you know I love you. Mwah. Okay, so we just finished chapter 9 in the practice of statistics, and so we're just going to do a little review video about hypothesis testing. So, promise it's not that bad. Hopefully, at this point, it's not that bad. um, so, the biggest thing to remember for hypothesis testing is that no matter what you're testing for, you're always going to have the same setup. You're always going to have to tell me what hypothesis test you're doing and why. Okay, so that's like you're stating. Um, and then second, you're doing your plan. So that's checking your conditions, and that's pretty much it. Checking your conditions, making sure you can actually do the test. And then thirdly, actually do your calculations. And then fourth, conclude in context. Okay, and I know we've talked about the state plan do conclude thing for a while, and you're probably getting sick of it. I'm sure you were sick of it day one. However, it's really important because on the AP, all of your free response questions they're usually 4 points for a reason, right? State, plan, do, conclude. So generally, if you show your work and don't get the right answer, you can get a lot of partial credit. If you get the wrong answer but don't show any work, you don't get anything. So that's why I really encourage you guys to always show your work. So anyways, I know it's a pain, but that's life. Okay, so general, state, plan, do, conclude. Okay, for stating, just make sure you include your hypotheses, your null hypothesis, your alternative hypothesis, what your significance level is, namely alpha. If that's given to you, great, use that. If it's not given to you, 5% is usually pretty good. And so you just want to include those and then state any parameters that you're using. Make sure it's in context because, everything's got to be in context because it's stats and it doesn't make sense if it's out of context. Ha! Planning, you're checking your conditions. Same one as we've always been checking, right? Same ones. Random, normal, independent. Okay, those are all your conditions. That changes depending on what your data is, but we'll get do step. If your conditions are met, then you want to find your test statistic, Z or T, and then also find the p-value. Okay, that's all you really have to do. And last but certainly not least is conclude in context. We reject the null hypothesis, we fail to reject the null hypothesis, we did have statistical evidence, we did not have statistical evidence, and remember, you're never proving the null hypothesis to be true. You're just getting enough evidence to either disprove it or not. Okay, so that's the big picture. That's in general. And then depending on what your data is, if it's qualitative data versus quantitative data, are you looking at differences or not? You're going to have slightly different tests. So let's just go through those more specific cases. So let's start with proportions. All right, so proportions are always for qualitative data. Colors, names of things, restaurant, types of meals. I don't know, anything that's categorical or qualitative data. Your null hypothesis and your alternative hypothesis are going to be that the true proportion is blank or is not blank, whatever the claim is. Okay. Alpha level depends on the situation, or you choose, and then you're stating what is actually P, not P hat. What is P? All right, so then you're planning random, super easy. Is it random or not? Normal. For normal cases for proportions, your test is not, the n is greater than or equal to 30. because that's only for means. This is the n times p, and n times 1 minus p have to be greater than or equal to 10. And independent is either the trials are independent, or if you're sampling, is your sample size less than or equal to 10% of the population. If the conditions are met, you move on to the do step. If the conditions are not met, you say, the conditions are not met, but I'm going to calculate it anyways, but please be cautious of making any conclusions because my conditions weren't met. So then your do step, when you're doing proportions, you're never using t, ever. So you're going to be doing the z distribution, so your test statistic is z, which is your statistic minus parameter over standard deviation of the statistic. In this case, p hat minus p all over the standard deviation of the statistic, which is the square root of p times 1 minus p all over n. Hey, by the way, you don't have to memorize that. It's on your packet. You just have to know what to use and when, which tends to be the tricky part. We can all use formulas. But just so you know, you don't have to memorize it. Okay? Make sure you find where that is on your packet. All right, next is computing your p-value. Your p-value is the probability of getting your statistic or anything more extreme. And so if it's a one-sided test, you're just finding the one tail. If it's a two-sided test, you end up multiplying whatever you get for your proportion, you multiply that by 2. So there's two scenarios for the p-value. This is one-sided test and a two-sided test. And for the one-sided test, you find the probability that z is either greater than or equal to whatever the value is, whatever your statistic is, or less than. And if it's a two-sided test, you just do 2 times whatever your probability is, whatever you get for your statistic. So, and last is conclusion. You either reject or fail to reject, depending on what your p-value is. If your p-value is less than alpha, we reject the null hypothesis because our data was statistically significant. If our p-value is greater than alpha, then we fail to reject the null hypothesis. Okay, for means, I'm literally going to copy and paste everything from the proportions and then just change what's different. Okay, what's different for means? Well, number 1, it's not proportions anymore. It's means, and it's for quantitative data. Number 2, our null hypothesis is not about a proportion anymore, it's about means. For the plan step, your random's the same. Your normal is the only thing that changes. Independence, still the same test. Normality, if n is greater than or equal to 30, then you're good. If n is less than 30, you have to draw a graph, and it has the sample statistics or the data have to be, you can't really have many deviations from normality, so no skewness, no outliers, etc. If we don't know sigma, which is usually the case, we have to use the t-distribution with degrees of freedom n-1. If we do know sigma, then we can use the z-distribution, which is a little easier to deal with, but generally the case is we don't have sigma, and so then that's your check for normality. Moving to the do step, if you know sigma, you have a z-distribution, and so you're just replacing your p's with x bars and mu's and all that fun stuff. Usually not the case, so generally we're not going to use that for means. If we don't know sigma, then we're going to be using the t-distribution, which is x bar minus mu, but instead of having sigma sub x over root n, we are using our standard error instead, square root of n. So that's your test statistic. The rest of it's the same. You find your p-value either using the z table or the t table, and then you conclude in context. Yay! Hey guys! Look what I found! Okay, the last kind of test we did in this chapter was the difference of the means. for differences in the data. So if you have paired data, you subtract them and find the difference. And the only thing that's different there is that your hypotheses are that you're looking at the mean of the differences. And you usually test that is 0, because that means there's no change if the mean is 0. And then we test, either there isn't a change, or the change is greater than 0, or the change is less than 0, depending on, whatever the data is. And then everything else is exactly the same. You just might have to calculate the differences in your calculator, put them in your lists, do it that way. And the last thing that we talked about was power and types of errors that you can make. So long story short, if you're just looking for this is how it is, alpha is going to be the probability of a type 1 error. And that's set ahead of time. So make sure that, as long as you have your alpha set at, 0.05, then the probability of making a type 1 error is 0.05. Then we call a type 2 error beta. And 1 minus beta is your power. So let's kind of refresh what all of those things actually mean. You have two situations, right? You have reality, and then you have whatever you decide, reject or fail to reject the null hypothesis. So if the null hypothesis is true and we fail to reject the null hypothesis, then we're happy because we made the right decision. The second possibility is that the null hypothesis is true, but we actually reject it. That is an error. That is bad. See, but the thing is, if the null hypothesis is true, which is the thing we assume to do all of our calculations, then when you make your sampling distribution, you're going to have your null hypothesis as your mean, and your standard deviation will be what you claim it to be. And the only chance of you rejecting it is what you set ahead of time, which is alpha. And so that's why rejecting the null hypothesis is equal to, right, making a type 1 error is equal to alpha. Because if your null hypothesis is true, the only way you're going to reject it is if you're in this region of rejection, which you set. Now, if your reality is that the null hypothesis is false, you don't actually know what's true, but you do know that the hypothesis is false. And so you can either, again, fail to reject the null hypothesis or reject it. So in this case, if we fail to reject, notice how I wrote fail to reject, so you remember that it's a type 2 error. Fail to reject the null hypothesis, we've made an error now because the null hypothesis is truly false, but we didn't reject it. That's a problem. And we call that error beta. Okay, so the first one was a type 1 error. Second one was a type 2 error. And now the other scenario is that we actually reject the null hypothesis when it is in fact false. Our null hypothesis is actually false and we actually reject it. So that's a good thing because we've made the correct decision. And that, my friends, is what power is. The power of rejecting the null hypothesis when it is in fact false. 1 minus beta. Now the tricky thing is we don't actually know what the true distribution looks like if the null hypothesis is false. We haven't tested, yes, we know the true mean is blank. We don't know that. We just know it's not our null hypothesis. And so that's when the new distribution comes into play with a new mean and, all that funny business happens where, oh, I'm rejecting the null hypothesis here and there. I'm making a correct rejection of the null hypothesis. So that's kind of like big concept, but in general, these are the most important things to know. So there you go. Good luck.